away so that he can go to his next meeting once he finishes here. So I'd like to introduce Dr. Ramesh Raghavendra from SEAM, down at WIT. SEAM is based right next door to Shivo, so we're neighbours and we're involved in some consortiums and so on and so forth. Ramesh.
Thanks so much, Ravi, and good afternoon, everyone. Anyway, actually, first of all, SEAM stands for Southeastern Applied Materials, right? So Southeast is Waterford, so that's where the name comes from. Anyway, I think you might have heard from Priyana about all the 3D printing. Okay, I'm going to talk about back to DMLS process, which is a direct metallized sintering process. And so I'm going to just start off with a very brief introduction, and then my talk is going to focus on the difficulties, right? What are the things which are required for 3D printing? Yeah? Because as you might have heard from Prerna, that it took almost 10 to 12 years to from the stage where they started and then to put into production, right? The reason why it took so long, you will see from my talk, right? What are the intricacies involved? Yeah. Okay, so first of all, I would like to start with a brief introduction about ourselves. As the name stands for, we are a Material Science and Engineering Research Center, and we are based in the School of Engineering within Waterford Institute of Technology in Waterford. Our center was formally launched in 2009, and we are part of a technology gateway network funded by Enterprise Ireland. Can I say we are seed funded by Enterprise Ireland, which is a nationwide resource for industry based in only in IoTs, yeah, delivering solutions for near-to-market problems for industrial partners. There are altogether 15 gateway centers in Ireland, distributed across all over Ireland. Of course, every gateway has got its own use applications. In terms of SEAM, right, what we do is we provide unique world-class professional services in terms of delivering innovative engineering material solutions, and also we create value-added competitiveness using the latest technologies to deliver real solutions for real problems. Yeah. So anyway, now what we do is that so these are the core capabilities, right? So we are the Center of Excellence for CT in Ireland. So through CT technology, we do a lot of product design optimization. For example, through overlaying the scanned CT data with the original CAD data, and then we can show the variances between the finished product to the original design. Yeah, and then we provide a lot of 3D metrology solutions using CT. And also we do a lot of finite elemental modeling using SEA, and also we have got CFD as well, which is computational fluid dynamics. Yeah. And then we do a lot of failure analysis of product components. In fact, if industry has got any failure related to materials or anything like that, no, we do investigation, then we provide mitigation strategies as well. Provide a lot of bespoke solutions for customer-specific issues relating to materials engineering, and then finally, like in the last 2 years, we are working on 3D additive. So we assist with over 100 companies, 110 companies throughout Ireland, and then we were awarded a KTA award last year for our industrial impact. Yeah, the industrial impact we created in our center. Yeah. Okay. Now let us move to the printing into a mass that has three-dimensional shape, and so you got a powder reservoir where we've got a rotor blade goes and then sweeps a layer of powder to a build plate, and then the laser selectively melts the region of interest, and it goes back, and again it brings back another layer. Yeah. So it is a bottom-up build process. Yeah. So the difference between conventional to additive, the name additive manufacturing is because in the case of conventional manufacturing, you take a big chunk of material and then you just machine it to get your required product. As a result, you got a lot of wastages. Whereas in the 3D printing process, now you build what you want. Yeah. So in that way, now the wastage is very minimum. Yeah. So advantages again, some of the things one of the key advantages now is designing the complex components, yeah, without adding cost. Yeah. That is one of the things, and then surpass limitations of conventional technologies. Yeah, there is a lot of products which you cannot build using conventional techniques. That's where the advantage is. Yeah. 3D printing is not going to replace your conventional lot of this low value, high batch process. No, it's not going to take over that. Where the 3D printing is going to have advantage is building complex components, yeah, and with high value and the small components, small batch, something like that. And then the other thing is that it is disrupting the supply chain. Wherever you require 7 or 8 assembly processes, that you can reduce it to 1 or 2 processes. Yeah, that's where the advantage of 3D printing lies. Okay, now let me talk about the design for additive manufacturing, right? In fact, for the design, you require a very totally new way of thinking, yeah, compared to the conventional manufacturing product, how the design engineers have been doing. So this requires a completely new way of thinking. First of all, additive manufacturing offers a high degree of freedom to design. In AM process, the complexity is not an issue at all, or it has got no impact on the manufacturing cost. So how this added value is achieved depends on the application. Maybe it could be a lightweight design through topology optimization, or a performance enhancement through a function-oriented shape, or the integration of functions into a single structure. Yeah. So the design complication doesn't come into picture at all. Yeah. And then the designer's challenges is that now you need to identify what you want, what function you want, yeah, a convention that will bring into benefit into a redesign process. And then, as I was mentioning you need to break with the roots of the conventional manufacturing. Yeah, you need to the guys who are all along doing a conventional design, right? They will find it difficult. Whereas a guy who is a fresh graduate, that person will have a much more advantage here because that person will not have the bad habits of over designing. Yeah, whereas in the case of additive manufacturing, it's generally it's under designed rather than over designed. Yeah, and to incorporate this new approach into the process of designing the product components. And one of the things is that now the 3D printing, right? There's a lot of focus will be requiring on designing the support structure. You cannot build a product directly onto a build plate, yeah, because of the heat transfer issues and various visual stresses. So you need to build a support structure. So a lot of efforts will be. If you are building a support structure, then you should remember that you need to remove the support structure out. So the design engineers have to make sure that whatever the support structure they are building, it should be less complicated. At the same time, it is useful. It serves the purpose as well. Yeah. So support structures are temporary metal supports built as a component. They is built to resist warping due to thermal and residual stresses. Support delicate structures during a build and also to provide heat transfer. Then, as I was mentioning, as support structures has to be removed during post-processing, some conservation of their location is important during the process. Yeah. Just to give you an example, conservation for supporting support structures. There are a lot of pitfalls, yeah, in the support and in the support structure building and the build techniques. Yeah. First of all, for example, if you take number 1, where you have a removability problem, if you are putting a support structure there to support that structure, you need to understand how you are going to remove that. Yeah. So these are the things which a design engineer should have in mind. Yeah. And then the heat transfer requirements, and then, for example, if you take number 8, yeah, which is a high solidity support, yeah. So these kind of, if you're building some kind of complex parts, the design engineer should be aware of all the requirements and intricacies involved in the support structure. So there's a whole area of work required to be done on designing a support structure. It's not like straightforward as Trina mentioned. It's not like buying a machine and you can print the parts. Yeah. And then again, if you are going to build a part which is parallel to the base plate, then instead of building a support structure here, you can build a kind of angular part. So in that way, you can minimize the support structures. Yeah. So this is why I'm telling that the design engineers have to think totally different way of designing. Yeah, in terms of building the parts. And again, the part orientation. If you want to build that kind of a cylindrical part, right, whether you are going to build horizontally or vertically or angular, yeah, the orientation is going to have an effect on your final mechanical properties or the properties of interest. Yeah. So again, that has to be taken into consideration how you are going to build the part, yeah, in what orientation. So again, thinking about the additive design. As I was mentioning again, I'm repeating that now. It's consider the function of a design and its critical design requirements, and build and you need to design based on that foundation. Build the component around these requirements and add material as needed to facilitate the functional necessities of a component. You don't have to add, for example, in a lot of conventional machining, there's a lot of they do over design. The reason being, and then they leave it as it is because in order to remove the unwanted part takes a lot of it's more expensive to remove the unwanted part. That's why a lot of material is left. Whereas in additive manufacturing, you got the luxury of building what you want. Yeah. And finally, add constraints as required by the material, as required by the metal AM techniques such as support structures and the rounding of sharp edges. Okay, this is a very classical example of building a conformal cooling. Yeah, the old design it used to be an assembly, whereas in the case of AM, you can make it using a single part. I have some parts if anybody's interested, I can show you, right? So because of that, your cycle time saving by using this conformal cooling is almost multiple folds of time savings, and also apart from that, you get a product homogeneity, yeah, to have a kind of a cooling coil, built-in cooling coil, yeah. So, and also the other advantage is like you can do design optimization through CAD, FEA, and AM. Yeah. For example, AM technologies provide great opportunities to reduce the weight of components and streamline design. However, where in the past parts would be to routinely over-design, it's now possible to under-design components. And the use of FEA modeling strategies can be used to mitigate this and ensure design robustness and quality. Again, it is, for example, that is a classic example. The left-hand side, right? this is a turbocharged rotor, and you can see the traditionally cold component typically are over-engineered, right? The reason why they don't remove this kind of excess material here, sorry. The reason why they don't remove the excess material here is because of the machining cost involved, yeah, so they leave it like that. Whereas with additive manufacturing, you don't have to print those parts, so the part is nearly 30% less white, yeah. So as a result, you are going to have a fuel efficient savings if you are going to, because these are automotive parts, yeah. So you are going to have a fuel efficient savings, yeah. In fact, these parts were built in seam, yeah, in seam, and then in fact now it gives the same performance as that of your conventional machine, yeah, conventional machine parts. Okay, so after design, okay, this is the build process. Okay, this is what we have in SEAM. We have a EOS M280 system. It is a 200 watt ytterbium laser. It can accept 3D CAD files, and the build volume is 250 by 250 millimeter, and also we can build up to 300 millimeter height, and ability to optimize material parameters. Yeah. So currently, we have printed maraging steel, 316 stainless steel, TI6ALB, and also we can print nickel alloy as well. In fact, we can print up to 20 different materials, yeah. 20 different composition. The processing sequence, of course, Train has already explained. In this one, you need to have your CAD file. And one of the advantages in SEAM is that, if you don't have a CAD file, right, we have a CT scanner where we can do a CT scanner and take the output of the CT scanner and we can use it as an input to the 3D printer, yeah. And then the data preparation, and then you build up the print, and then you get your post-processing. It's very important, the product which comes out of 3D printing process, you don't get the same surface finish as the conventional machining. So there are post-processing requirements like a shot peening or electro-polishing or whatever it is, depending on the surface roughness requirements. And then, okay, we have got various characterization or validation techniques available. We have got, for example, a particle size analyzer where we can check all the incoming powders. And then we have what we call a post-processing equipment, and also we have got what we call a white light interferometry, where it can non-destructively evaluate or a non-contact technique to measure the surface roughness. And then the heat transfer is required with heat treatment, for example, for some of the parts. If you are building a titanium parts, as you know, it's very prone to warping and the residual stresses. So you need to heat treat that in the as-built condition, yeah. And so the validation techniques we have are the CT scanner, which I will mention to you, that gives the product integrity, metrology, and nominal comparisons. In fact, as mentioned at the start, now we are the Center for CT in Ireland. We have two CT systems. One is a 180 kV nanotron system, which is primarily used for polymers and low-density metallic materials. And then we have a 300 kV system, which is primarily used for high-density metallic materials, and also we can use we can scan parts which is almost 2 foot height, yeah, or 60 centimeters height, yeah, and also very high-density material, yeah. The key features, it is a non-destructive. It can visualize objects in 3 dimensions, and once you get the CT part, you can characterize for voids, defects, warping, delamination, coordinate measurements. So this is a very powerful tool, which we have to characterize the integrity of your 3D printed parts. Yeah. And this is a nominal comparison. For example, the left-hand side is a CT scan part, and which has been overlaid that with the original CAD file. And the right-hand side, you can see the nominal comparison which has been made. Yeah. All the green parts are bang in the middle of the spec, and blue regions are below spec, and the red regions are above spec. Yeah. So we can compare the CT part to the finished part of the original CAD file, and we can provide the variances of that. Yeah. So other techniques, then we have a scanning electron microscopy technique to find out if there is any inclusions or anything like that, and then I mentioned about the RA, and then we have a lot of other mechanical characterization techniques available in-house. Yeah. So in terms of additive manufacturing, right? So we are an applied research center, right? If anybody is interested in trying to do a feasibility study, and because we are not a manufacturer, we don't produce products in bulk. Yeah. If anybody is interested to do a feasibility study, projects like how it's going to behave or anything, then you are talking to the right person. Yeah. So we now offer a full design to prototyping service. Yeah. We can design, optimize, and if you don't have a CAD file, doesn't matter. We can do CT scan, and we can extract a file, and then we can build products. Yeah. And then we've got the various validation technique, and we can validate how good the part is, and we can provide the parameters. Yeah. And then it's up to you to go and manufacture whatever it is. Yeah. So we offer full design to prototyping service. So that's all it's about my talk. Yeah. So thank you.
Ramesh, thank you. three of us spoke at some length about what Striker are doing, and Striker are really flying the flag for Irish innovation within this field. But you guys have been working now with DMLS for quite some time already, and I'm wondering if you've seen a lot of interest from Indigenous companies. Can we expect to see a lot of Irish companies wanting to use the technology more, maybe invest in the technology?
Absolutely. Absolutely, I think. Now, in the last 1 year, we have seen a lot of interest here. Because at present, right, I mean, because we only have one machine, actually, we have a kind of bottleneck, yeah, so we can only take so much project there. But having said that, we are already thinking about going for a second machine as well, yeah. So as we develop, I think in a year's time, we'll be adding a second printer as well to assist industries, yeah. I think definitely for complex geometries and building geometries, no, this is the way to go about it. And we are there to just build up all the initial parameters and everything for the companies to go and make use of the technology.
Any questions from the floor for Ramesh? Thank you.
You just mentioned about the materials. Can you use stainless steels? You can use high nickel alloys.
Yeah.
Are they in powder form?
They're all in powder form. The powders what we use is roughly in the region of around 30 to 40 microns.
So metal powder 30 to 40 microns.
That's right, yeah. But if you want finer powder, there are machines available, but our machine is only capable of around maybe 20 to 50, 60 microns. Yeah.
And when you polish, what kind of surface finishes can you get down to?
See, for example, now we get, for example, in terms of marrying steels, we got around 8 microns, 10 microns, but we can bring down to 1.5 to 1 micron. But if you need still further, if you want to still reduce further, then you can go for electropolishing technique.
Electropolish.
Yeah.
Great. Thanks.
Actually, yeah. If anybody are interested in visiting SEAM, right, you are very welcome. We are based in the. I don't call it anymore Sunny Southeast, yeah, because I had a very, very bad experience. Last time we had a technology gateway managers meeting in Waterford in December. The amount of rain we had that day, my goodness, nobody has found such kind of rain. So I only call it as a southeast rather than a sunny southeast. But you are all very welcome to Waterford. It's a lovely place, and we give a line tour, and I can even give a workshop or whatever it is. Yeah, so you really can do that. Yeah, and then Shivo is by the side as well. Yeah, you will have an opportunity to visit Shivo as well. Yeah, thank you.
Come on, come on. Waterford.